C. So A and B would have the same total electric field, and then C,
Be the same, right?
it would still be the same.
It'd be until like the last one.
So that's what A, B, and C, and initially.
Oh wait, no, that is the same.
What about from the plates?
Sigma over epsilon sub 9.
Sigma kind of looks like a turbo.
And what's sigma?
Charge over area.
So we know charge area, 100. So Q, so just for the first one, 2.655.
Yeah. Times 10 to the negative 7.
Over 100 square meters times 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared.
1.05 times 10 to the 10th.
No, I don't buy that.
Alright, check again. Oh, I did the charge for 9.2925. I did not do the charge as 2.655.
You just divide it by 3.5 then, right?
Divide that by 3.5? No.
$300.
Yeah. If there's no dielectric, my electric field between the plates, because of the plates and the total is the same. Dielectric is what changes that. So we should be getting the exact same value as we had for the total to start out with.
Oh, it is 300.
Now when you stick the dielectric in, we're building up charge on the plates because it's still connected to the battery. And so we should be getting a much larger value now. So my electric field for part A then, because of the plates, well, I increased the charge by 3.5. The denominator, that hasn't changed at all. So this will be that times 3.5.
So, 1,050
Yeah. Finish it off.
newtons per coulomb.
Why did you give it 1050?
It should be that times 3.5. Because the charge increased. The charge increased by a factor of 3.5.
So could you just say it's in the formula? Could you add kappa to it?
If we're gonna do kappa, no, the kappa wouldn't show up here. The kappa would show up here. That, I'll squeeze it in, different color, stunning visual effects and all that. Okay. The electric field between the plates, sigma over epsilon, which is sigma over kappa epsilon sub naught. So this should get you the total. Because kappa increased by 3.5, that's going to increase by 3.5 in order. My train of thought just got lost there, so let me back up. So if you're gonna do 3.5, so kappa times from, this is total. Kappa times the total electric field strength would be sigma over epsilon naught, which is the electric field strength from the plates. After I've done that, I'm not quite sure I really enlightened anything there, but, it matches what we've done down here. Whether you believe it or not, but it's true, true story. So I find the electric field between the plates by sigma over epsilon, not just recognizing my charge increased, or I could just take my total and multiply times kappa.
But it's what we did, right? We just.
Yeah, so that times 3.5 gets you that.
Why do we use kappa? Like what is K usually used for?
Constant.
Oh, why kappa, not K? We also use K for the electrostatic constant or Coulomb's constant. K is used for
Kelvin.
the capital K, capital K for kinetic energy.
Oh, yeah.
Just ignore me.
Lowercase k for harmonic, the spring constant.
Oh, yeah. Dang, so you really couldn't use either of the Ks. Kind of like how they already use C for, the two C's that we were just figuring out. For capacitance and.
Oh, C, I heard C.
I meant C, my bad.
Yeah, we use C for two,
So we
capital
can't
C
use-
for two different things.
So we can't use C for charge. We use Q for charge.
It all makes sense.
I don't think it does.
I agree.
So what do we use like Z and Y for? Like the more obscure letters?
Oh, we can't use those because those are our
Axes, yeah,
variables.
axes.
Yeah.
We'll use capital Z later on.
Okay, never
For if we.
Okay.
So if it's a capital Z, do you put two lines through it or just one still?
For what?
For a capital Z, do you put one line through or just two?
I just try to make
Or
it
I
look
do-
bigger.
Oh,
There was something where I did run into, I was using a capital Z and a lowercase z, and I think for the capital Z, I put that there and then the lowercase z.
You know what? I figured it out. We have to put lines underneath. And that's how we can distinguish between all the same variables. And then you can change the lines. You can make it like a squiggle, you can make it like a very sharp line, or just a straight line, or a dotted line.
All right, here's how you do it. Get in a position of power in the physics community.
And you just had to use stuff.
Gonna make the rules.
How do we
Start
do
using
that?
Spanish
letters.
I don't know how you do that, but
I think you start like writing physics textbooks and start editing them and start changing it over time.
There you
go.
Like,
So you seen-
molding the next generation up that are just like.
You seen how they-
Squiggly line.
I like
You
that.
seen the letters in Spanish with the little like squiggly on top?
accents.
We can get into those at some point.
Wait, Dr. Fox, you're in a physics textbook. Why don't you do something about it?
He's in it, he didn't write it.
I'm too old. I'm too old for this. The thought of there, occasionally I've had delusions of writing a physics textbook, and then I think about coming up with 100 different problems, and I think, yeah, no.
But
Physics textbook with no problems whatsoever.
You've already come up with a lot of problems.
Just copy and paste.
Yeah, just use your master set problem.
Yeah.
All right. So that's the end of the first one. Any questions on number one?
Oh,
It all
sorry,
is
did
for-
we do part C of finding the electric field of the plates?
Oh. Yep. All right, so that was A. B is the same. So what happens in C when we expand the distance?
Is that total multiplied by 3? Or do you divide that by 3?
Want me to divide them
I
by
think,
3?
yeah.
All right, so we got a couple different, let's look at this formula right here. Did the charge change from B to C?
No.
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 Did the area change?
No.
No.
Did epsilon sub naught change?
No.
I
The
would
answer is
not.
the same.
So, none of that changed.
So everything's the same.
No, but the question was, what happens if you change the distance, right?
Yeah,
It would, if you increase the distance, it would decrease?
But it's because it's just the plates, whatever comes from the plates, as long as you don't change the size, it's the same, pretty much.
yeah, because we're doing the infinite plate approximation, that the electric field does not depend upon distance.
Oh. So
So-
nothing happens?
Pardon?
So nothing happens?
The electric field between the plates, because of the plates, stays the same.
Okay.
If you're looking up here, again, the charge is not changing because we disconnected the battery. Epsilon sub naught's a constant. Kappa is still 3.5, that hasn't changed. We've already established this will be 300 volts across the board. So, nothing's changed there. If you want to use this formula, so you pretend the dielectric's not there, the concentrate on the plates, that's 45 volts. That's now 3 times what it was, but that's been multiplied by 3 from the original, that's multiplied by 3 from the original, so that doesn't change. So there are a lot of ways of coming around to the same place and checking yourself. And there was one unfortunate test where I gave too much information so that you could get different answers depending on which path you took. That was fun to grade. All right, any other questions on number 1?
Actually, I was gonna ask, on the test, can we request equations for the, like equation sheet in the front? Or is that just whatever you have, that's what you're gonna put?
Is there something you want me to add to this?
Yeah, could you add, I believe, electric field from plates, so Q over epsilon sub naught over area, or sorry, Q over epsilon sub naught area, and then also for electric field as voltage over distance, and then I think you have the other 2 relationships.
They're not on here.
Yeah, you have the other 2, so.
Oh, there's a contradiction in our chapters here. Under physics formulas, I have 27, 28, 29, and at the top I have 29 through 31. Apparently, about the time of transition between the 2 books.
Well, the bottom formulas seem more centric to our curriculum. 29 through 31.
Yeah, oh, agreed. But, yeah, there's some formulas that I'll have to double check. It feels like there's some formulas missing, but. Okay. Well, some variation of that. Yeah.
What's that weird version of resistivity on there?
Sorry, again?
There's like that one weird equation for resistivity. It's like 1 over charge density. Well, it's not charge density, but it looks like it.
Let's see where.
It's like
Oh,
ME divided by NE squared T.
oh, that row right there in that sigma are not densities. That row is resistivity and that sigma is conductivity.
Oh, okay.
And that's equal to the mass of the electron divided by the number, the charge carrier density times the charge of an electron squared times the mean time between dividing the things.
Oh.
Not for test.
Yep. So just watch out for that, that even within this test, sigma is gonna be used for 2 different things. Right. Other questions? All right, let's let's take a look at number 2 there. We have 7 identical capacitors that are put into parallel. Total capacitance is 42 nanofarads. What's the capacitance of each individual capacitor?
6 nanofarads.
When you put capacitors in parallel, did I say parallel or series there?
You said
No,
parallel.
Parallel. So in parallel, we just add them up?
Is that how that works?
Well, that's what I was asking you.
I don't think so. But I really don't know.
So in parallel, so we got.
So in parallel. Okay.
I say that's 40, the equivalent capacitance of 42 nanofarads. So capacitors in parallel, they either add up straight as, or you add up the reciprocals and then take the reciprocal at the end. It's one of those two.
The reciprocals for series, right?
That sounds right.
There's a lot of hesitancy there.
Can we do like both versions? Just for clarification.
I'll do both versions, but I'll set up the other one. So it's, one's like that, and the other one is like this. All right, for capacitors, think about if I have a huge plate and I cut the plates in half, so now I have 2 smaller capacitors,
Okay.
but it still holds the same amount of charge for the same voltage. So the total charge that is, yeah, the total charge stays the same. If this is just an adding up. So it is indeed 6 nanofarads. So 42 divided by 6.
Oh.
Divided by 7. So that's just the sum.
You can leave that one in. And,
Over here, you're adding up the reciprocals. So I know that 1 over the equivalent capacitance is equal to the sum of 1 over the individual capacitances. So this is 1 over 42 is equal to, well, they're all identical, so I have 7 times 1 over the individual capacitance.
which is. I see.
94.
And that would be if it was asking if it was, they were ran in series?
If they were in series, this would have to be the individual.
Okay.
Now, another way you could check it, if I've got a capacitor placed this close, and then I make them farther apart, what happens to the capacitance?
Goes down.
Yeah. So if you could think about this as,
One big capacitor with a big space in the middle.
and the space in the middle is just the sum of all of these spaces right here. Assuming all the plates are the same size and so on. And I was thinking, one of the videos I went through that, or maybe I just imagined it.
Went through which?
The showing how this series is just it's basically, you can think of it as one big gap between them. And you just have to stick conductors in the middle. William?
And for resistors, this is flipped?
Yes.
Gotcha.
So, if, let's just say you asked like the same question, but instead of capacitors, it was resistors, we're just switching the process.
Yeah. So if they were ohms, if this was 42 ohms, this would be 294 ohms each here, and then 6 ohms here.
Like this, that one, it was in parallel,
Yeah,
and those are in series.
correct.
Okay, just clarifying, thank you. All I can imagine is a big old camshaft with that's like 7 cams. Don't know why.
Does it help you?
Kinda, but.
Okay. All right, number 3. Just a simple ranking. What's an EMF, by the way?
Electric magnetic field.
Nope.
I don't remember.
I've learned that.
I went through the videos of 28, 29, 27. I did not come across EMFs.
Oh,
I thought that was, I'm pretty sure that might be chapter 30 listed on Blackboard. I could be mistaken, but I'm fairly certain.
I feel like in any other medium, EMF does mean electromagnetic field.
But is it,
generally you would say electromagnetic field, but
Yeah.
I generally see that just as EM, capital letters usually.
so does the F force, maybe? I don't think it'd be force. But.
All right, so EMF originally stood for electromotive force. Electromotive force. It was the idea that it was the force which drove charges to move to create a current. At some point, they realized it's not a force, it's a voltage. And it's the potential difference which causes the charges to flow. So even though some textbooks will say EMF stands for electromotive force, I would contend, and I do have some support for this, contend that EMF no longer stands for electromotive force. It stands for EMF.
Just EMF.
Yeah.
I mean, that makes sense, because you're saying that the old word has been proven wrong, essentially, or.
Right, yeah,
Or it's a
or it's
misleading
misleading.
term. Okay, because that kind of sounds like they're treating it like water, you know? Enough force and then it makes it go, kind of thing.
Yeah, and, I mean, ultimately, you can find a force acting on these things, but it's not that number.
Okay.
All right, so EMF, you can think of EMF as an ideal voltage.
Okay.
I got a 12-volt battery, I hook it up, I'm not gonna be getting the impact is not gonna be 12 volts because there's some internal resistance in the battery. And so the EMF is the 12 volts, that's the ideal, assuming no internal resistance